a little different. So this is not the circuit. So let's go ahead and make modifications to the circuit so it matches the one that you have in your lab book. So what's R1 in your lab book? We're on figure. I don't know what figure it is. Like I said, my lab book is different than y'all. So we're at the circuit. So what page is the actual circuit on? We're supposed to wire up. Page 283. So we're there? Everybody there? Yes, no? Well, this circuit is, it's different, yeah. So the circuit is different. I didn't, so this is a 47K. Okay, and then what's R2? 10K. And then what's RC? They call it 6.8K, 6.8K. And then R1? I mean RE, I'm sorry. 2.2K. And then we have a load out here. Yeah, 10K. And what do they call it? RL? Yeah. Huh? From 30 table 34 what? Yeah. So y'all not, yeah, y'all's is okay. It's just the search that I have. It's not exactly the same. We'll do the table. I got the circuit wired up. Oh, okay. This is this is the table that we work out. Change it in. Okay. Now we got a problem in that on theirs they have 1 volt peak C, and then they're bringing this out, so it's an AC source, and then they're bringing this out and going to a voltage divider, fixed voltage divider. And what size resistor? So what we're going to do is we're going to bring an AC input in, but what they're shooting for right here is we're shooting for 10 millivolts peak C. You know what it says? I know what it shows. Well, somewhere in the procedures it says adjust it till we get 10 millivolts. Now, of course, this is a voltage divider. What size is this resistor right here? The circuit, what page is the circuit on? Not the instructions, not the table. What page is the circuit on? Okay, so turn the page, Mario. That's the circuit. Okay, now, so what size on this voltage? So I got a voltage divider because they're saying, okay, the only thing we're going to put 1 volt peak over here. So let's say it's 1 volt peak C. Yeah, so what is this going to be? That is 10,000. Okay. And what's this one? 100K? No, 100. Oh, $100. Yeah, that makes sense. So what would be my vote be in? Yeah, it's the bottom one, because this is circuit common. So this right here, this bottom one is actually setting the voltage, right, but it takes 2 of them. I'm looking at 9 millivolts for PM. So how'd you do that? I did 100 divided by 10,100. 10,000. 1 volt. Good. Time for one vote. No vote. Not 10 no votes. Okay. The problem I have is when I come over here to this, I could use this function generator or this function generator that's on the trainer. So when I come over here and look at the function generator on the trainer, over the trainer. Okay, so here's my scope. And I'm going to turn it all the way down. So this is my amplitude. I'm going to turn it all the way down. And that's the best I can do. Now the scope is picking up a lot of noise. When you get down to these very, very low voltages. So the best I can do is about 15 millivolts. Okay, how would I get it down to 10? I can't use this voltage divider right here. So I can't use this voltage divider right here. So what I'm going to do is I'm going to come up here and write this. So that don't work. How can I set any voltage I want to over there? For what? Use a pot. Good. Great, guys. So instead of using the voltage divider, I'm going to use a variable voltage divider, and I can get whatever voltage I want to, right? You understand that? So we're going to modify the circuit, and we're going to come over here, and we're going to take our function generator, which is the trainer, it's variable, and then I'm going to come over here, and I'm going to run it through a potentiometer instead of a fixed resistor. And now I can set whatever voltage I want. So good call. That's good, guys. So I'm running to a 10 pot. So I modified this pot. Now I can set any voltage I want. Are we okay? So here's my circuit. I'm going to discard it. I'll come back and redraw it, and then I'll keep it. So let me switch over to my camera. So here's my circuit, and I spread it out. You can make it a lot smaller, but I spread it out so we can keep it a lot better. Here's my transistor. It's a 2N30. It's a 2N 3904, which is an NPN transistor. Emitters on the left. So here's the emitter on this side. Here's the collector on this side, and the base is in the center. No, you couldn't even with that signal generator. That signal generator won't go down to about 2 volts. So if we use the signal generator, we would have to use a pot. The trainer almost gets there. This trainer almost gets there. That signal generator puts out almost 2 volts when you turn it all the way down. And what's nice about a signal generator is that it's got a frequency counter in it, so it actually shows you the frequency. Here we're going to look at our oscilloscope and let our oscilloscope figure out how to set the frequency on the oscilloscope. So good point. Yeah, so I could have used this over here, but it was since I was hooking up my circuit on the trainer, and the trainer's got a function generator on it, it just made sense to do that. But that's a good point. So I would have still had to use the pod if I used the what? Signal generator.
So we said so we'll have to use that piece of metal.
What do you mean? We don't set the frequency on the scope. The scope measures it. I've seen people do that. I said, I want 5 kilohertz, and they're up there messing around with their scope. And I said, that's like making I want 5 volts on a power supply, and I'm up here messing around with this messing around with my volts per division on my meter, trying to get 5 volts. Well, these are test equipment. They measure what's there. Does that make sense? So I'm going to set the voltage with my scope. So let's bring my scope back up and hook it back up. So here's after, this is after my pot. So I'm gonna turn this up a little bit so it makes it a little easier to measure, not the frequency rich. So, and then I'll come up here and set it down to 10 millivolts, which would be roughly one division. I think we got a 0.5 on this. Let's see. Two divisions. And it's going to be hard for the scope to trigger on that because it's got so much garbage in it, right? But you can definitely see that's two divisions. I got it on 5 millivolts per division, and that's the best the scope can do, so that's 10 millivolts. Are we okay? So let's go ahead and let's calculate our bias. So we got the resistor there. It fell off my lap. So they want us to calculate. Now turn the page. Now we need to turn the page back. We're not going to measure any of our resistors. In this class, we don't measure resistors. The only reason in this class to measure resistors is if you can't read the color code. Yeah, so we're not going to, so measured values, we're just going to mark that out. And we're going to use the color coded values to calculate our voltage. And then we're going to calculate VE, we're going to calculate VB, VE, IE, DC, and DCC. So y'all go ahead and do that. And then we're going to come back and measure and see how we did. So I didn't want to do that. Well, we might, when we're playing around with a circuit, we might move it around, but for calculation purposes, we'll. Of course, we're not going to measure IE. We can calculate IE, but we're not going to measure it. We can filter that. You talking about a table or a figure?
So calculation you both divided to get R2.
You got everything you need. VN has nothing to do with calculating the DC levels. So VCC is set at 10 volts. But we can do it on here. So now I can get to it. So what I'll do is I'm going to erase this. So whichever way you want to do it, it's up to you. You can do RT. You can divide RT into 10 volts. And then you could take that and multiply it times R2, and that would give you the current, like you learned in DC. But what we find out, it's a lot easier to use what we call the voltage divider.
divided, 10K divided by 57K times 10.
Hold on, let me write, okay, so that's gonna be 10K divided by 57K times 10. You can just drop the K's off because they're on top and bottom, right? So 10 divided by 57 comes up and gives us about 1.75 or something. So that's going to be VB. So VB equals VR2. Okay, then I can come over here and get VE. So VE, yeah, it's going to be equal to 1.75 minus 0.7. So VE is going to be equal to 1.75 minus 0.7. And now we're back to on clock. So that's the only thing you had to know, right? That was different. So that's going to give us 1.050. That's going to be VE.
You divide that by RE.
Oh, yeah. Now we know the voltage drop across RE, and we know the size of RE. So IE is going to be equal to 1.05 divided by 2.2K. No. What's that? 400? So VRC, since this is a series circuit over here, we just don't know the resistance of the transistor right now. Would be equal to R, V is equal to I times R, so it's going to be 6.8K times 477 micro. And that's the problem right there. Okay, so what's VC going to equal to? Yeah, VC is, that's what we're concerned with. That's the output of the transistor. So VC is measured from here to here. No, VC. This is VC right here. This is VB. What's that? I know it's going to be at least 6 volts. VC, I'm measuring from here to here. So the only thing that I'm getting is I'm losing the voltage drop right here. So if I was to come over here and redraw this circuit, or vice versa. You can say minus 10, but remember the answer is going to be positive. So what I've done is I've calculated this resistor right here is dropping 3.4 volts. I'm not measuring that resistor. VC is measured right here. So I've dropped 3.24 volts. So what's left over to drop on the other two devices? On the other two, huh? Everybody understand that? This is DC, guys. So if this resistor right here drops 3.24, so I've got 10. This drops 2.4, so what do I have? 3.24, so what do I have left to drop across the other two resistors? Well, now I can calculate VCE. So VCE is going to be equal to voltage on the collector, which is 6.7 volts, not volts, minus the voltage drop on this guy right here, which is 1.05, and that's going to give me voltage collector to there. So VCE tells you the formula. So 6.7 volts. Is this transistor circuit? Is it operating towards saturation or is it operating towards cutoff? It's in the active. So I got 10 volts to work with. And I'm trying to put AC into this thing. So I got 10 volts to work with. And this is 0 volts right there. And so what I'm doing is I'm adding and subtracting from my DC. Where would I like to put what would I like to put that collector voltage at to get the max, so I can put the maximum into it, and the maximum out, to get the maximum output? So I'm putting, right now we're setting our 0 is up here, our 0 is up here, our 0 is up here at 6.7 volts. So I'm going to try to make this swing. So what's going to happen is I bring an input up. If it gets up to 10 volts, it's going to come off because it can't get more than 10 volts. And then I'm going to be able to swing down here, right? You understand? So what we would like to do is we would like to bias this thing directly in the center of what I've got right there. So so we're biased toward cutoff. So if it's above center, we're biased toward cutoff. If it's below center, we're biased toward saturation. So where would I like this thing to be biased at? I like to bias it at plus 5 volts. So how can I do that? Well, what can I change in here to cause that thing to get at plus 5 volts? Anybody got any idea? Hey, change the transistor. Don't deal with the resistance. Anybody got any idea?
I did the math, and I got 6.5 volts.
Where? No, we're trying to get VC. We're trying to get VC. So I don't know what VC is. VC is 6.7 volts. We want to get it close to 5 volts. We're trying to get it close to 5 volts because the output is developed right there on the transistor. So let's look at the beta for a 3904, which is what we're using. I'm going to bring up the data sheet. Data sheet.
Question is, if you don't know VA, this calculation of having
So here's the beta of 3904. Here's the beta for 3904. All we know is going to be somewhere between what? 30 and 300. Now over time, we've played around with 3904 a long time, and unfortunately, this data sheet, the typical beta of a 3904 in this circuit is around 100. So in it, we try to stay away from beta as much as we can because of why? Because what? Yeah, it varies. Now we can calculate the beta of this. So what we've done is we've set the beta of this circuit. So how would I figure out the beta of this circuit? No, we'd have to measure. We can't do that. Yeah. We know IE, but we don't know IB. We know IC. So we calculated IE, but remember, we're going to assume IE and IC are what? are equal, right? Even though they're not. So like I said, if you see on test 3, if you see a question that says IC equals IB, you're going to say, we're going to say IE equals IC, that's going to be false, right? You understand? If it says approximately, then it's going to be true. So no, we don't know beta. Well, like I said, for this transistor, beta is roughly 100 for this circuit. But if I was to, and it's not, once beta is set, it's not going to change with temperature anymore. Why is it not going to change with temperature anymore? What resistor in there keeps this thing changing, the beta from changing with temperature? So we actually looked this up. I hooked up a little switch, I put it in the middle, I brought a soldering iron up to it, and the voltage dropped across the transistor, started going down, right? So this guy right here, as soon as we set this right here to 1.05 volts DC, beta can't change anymore. Because if beta tried to go up, this resistor right here would try to drop more voltage, but it can't because it said it was 1.05. If it tried to go down, this guy here would drop less voltage, and the transistor would automatically turn on more, right? You understand that? But what we can do is once we establish the beta, the AC signal, temperature can't change it, but the AC signal can change it, which is really neat. So RE, that's your temperature stabilizing resistor right there. That's the function of that resistor in life, is to keep this thing from beta from changing with temperature. It's pretty cool. Okay, so I bypassed it. We got a gain of 80. We figured it was going to be around 130, but we got a gain of 80. Well, 85, right? So the 10 millivolts in is really neat. So 10 millivolts, I have it on 5 volts per division. We got 2 divisions. My output, I've got 200 millivolts per division, 200, 400, 600, 800. Each one of these would be worth 40. I'm sorry. That would be 240, 280, around 285. So I measured that wrong. When you go in 2s, then each minor division is going to go in 4. Y'all understand that? So what are we supposed to do now? Well, what we're going to do now is we're going to load the thing with our 10K. What are you going to expect the gain to do when we load this amplifier? Do you think the gain's going to go up, or do you think the gain's going to go down? Yeah, it's going to go down. Because now, right now, that 10K, or that 6.8K is not dropping, it's only dropping the current required by IE, right? You understand that? So here we go. We're going to put this guy in here. Here's my 10K. I'm going to put it in parallel with my, what's our output? 6.8K collector. I think a little tiny. So we got a 10K load. So now we're getting, so this is in the book. So we're getting a gain of, I still have 200 millivolts per division. So 200, 400, 40, 80, 500, 540 millivolts. Let's count that out. So it's 12.2468 times 200 millivolts per division. So this is the alpha 10K. This is with. It's something different. Is it not? I gotta take a 10-minute break. Let's figure out what I did. 10 minutes, right? Uh, when I was messing around up here, I accidentally pulled out my, plus 10 up here. So where we at in the lab? What do we need to do next? RE prime was computed. Everybody okay there? Huh? RE prime was computed. Be like 57 ohms. 52 ohms? Okay. AV. So AV. Well, no, because we got it bypassed. So what happens is we came over here and added a load. So let's calculate it with a load. Tell them where that formula's at. It's on the front page. What page is that on? What is the... I know what it is. Oh, yeah. I marked it out. That's right. This, I don't know why it jumps across like that. So we're going to put 6.8K in parallel with 10K divided by 52.
I got
78. And what unit is that?
8.
Is that volt, ounce?
8 doesn't have,
Doesn't have. Good. That would be AD.
that is the sum over, the sum over product over time.
You can enter whichever one you want to. Normally I do the reciprocal because it's just easier for me to enter that way on my calculator. And this is K, by the way. One, eight. In fact, on these, that's it clear. 800. Now around 77. So here's our measured gain. So I have my input, I've got it on 5 millivolts per division. I've got 2 divisions. My blue one is, by the way, notice the signals are 180 degrees out of phase. We got a little phase shift in there somewhere because when the transistor cuts on, the output goes down, right? So when the input goes positive, transistor cuts on, which means the voltage across it goes down. So this is a feature of the common emitter amplifier is the input and the output are 180 degrees out of phase. So I've got it on 100 millivolts per division. So that's 1, 2, 3, 4, 5.246, 5.6 division. So what would my measurement be? Everybody okay? About what? You only calculate 7 to 8, but it's guys, I've never done this where it's always lower because that's an approximation, right? And it's usually pretty good. So this is loaded. The bottom one's not quite on that thing. What I'm gonna do is I'm gonna take my yellow one and get it out of the way because we know it's okay, and that way we can see it real well. So I've got it on 100 millivolts. I've got it on 100 millivolts per division. 1, 2, 3, 4, 5.2, 0.4, 0.6. So it's 560 millivolts, right? 56. 56. The gain? 560 divided by 10, right? Yes, so? You okay, Martin? What's that? What do you mean should be? Okay, but what I'm saying is calculations are perfect, but our circuits are not. So we got 560 out, we got 10 in. 560 millivolts out. So I can do that in my head. That's a gain of 56. That's the measured value. Yeah, the computer we said, okay, well, we're going to have what? 70, 78? Yeah. So the computer we said was going to be 78. The measured is 56, which is really good. So V out, we put 10 millivolts in. We're getting what? We said we was going to have a gain of 75, so that means I was expecting what? 750 millivolts. That was my computed value. Okay. And then my measured value was 560. So here's not asking, so my gain, we calculated 75. We measured a gain of 56, right? Are you okay? Rn. So let's compute Rn. So what we're going to do for this transistor is we're going to assume a beta of 100.
So would that difference not be super alarming? Because you remember you said sometimes
Not for this one.
you part and then you go to measure and you see different and you know it's wrong. So with 70, like the 77 to 56, that wide gap is not too alarming.
No, it's not too alarming.
Okay. Got it.
Because it's gain in, understand what I'm saying?
Okay.
So that's good. Okay, so here's what we're going to expect on Zn. So Zn or Rn would be equal to R1 in parallel with R2 in parallel with beta, which we're going to use 100 times Re. So I would start with this over here first. So we dropped our input impedance down a lot. It's by bypassing that. So it'd be 100 times what? What was our 52. And I'm going to take the reciprocal of that plus 47,000. Take the reciprocal of that plus 10,000. Take the reciprocal of that equals take the reciprocal of that. That's got to be wrong. I got less than wrong.
Yeah, I think over 3189.
Which sounds right. So 100 times 52. What was RE prime?
Oh, yeah, that's
Equals that. We'll take the reciprocal of that plus 4,700. 47,000, yeah. Take the reciprocal of that plus 10,000. Take the reciprocal of that. It equals. And take the reciprocal of that. So 3,182 ohms, that's what your input signal sees. Now, a while ago, what are we using down here? 2.2K. So unbypassed, that would be 2,200 times beta. I'm sorry. Yeah. 2,200 times beta. Now, don't write this down. We're just going to see the difference between bypassed and unbypassed. Equals that, reciprocal. Then I'll do 47,000. Well, I didn't get plus. That's a crap rate. So we went from 8K down to 3K. So this is not, we're not writing this down. What I was going to show you is we changed the input impedance a lot, right? And what's important about the input impedance is whatever speed it is going to exceed this opposition. So that's less than half. So that means my input signal would have to supply twice as much current if I bypassed it over if I did not. But what do we get when we bypass? Well, we get a real high gain, but we lower our input impedance, right? You understand? What do we get if we don't bypass it? Well, we lower our gain, but we get a higher input impedance. So that means if I've got a device that it's got a high output impedance, I would feed it into a what? I would feed it into a unbypassed, so it don't have to supply as much current. And then the output of this one, I might feed it into a bypass, right? Does that make sense? So normally in stereos, we go through stages.
keep the gain lower.
The gain is a lot lower. So we went from a gain of 3 to a calculated gain of 75. Measured 56. So that's a lot of difference. So the input impedance more than half, right? You understand that? So you got to understand something is feeding this amplifier. And the lower the input impedance, the more power the signal that we're trying to amplify is going to have to provide. So that's what I'm thinking. Think about the antenna of your car out there. How much voltage do you think you get out of that thing? If you load that thing at all, you're going to get zero out of it. Your radio wouldn't work. So we want the amp, we want that antenna to feed an extremely high input impedance circuit. So we wouldn't use a bipolar transistor, or we'd use another type. So we should expect around what? 2,000? What y'all bet? What did we calculate? I need to write that down.
3189.
So how am I going to measure that? Well, we can't measure that because that's a dynamic resistance. So if you disconnected everything, you put your ohm meter on it, you're not going to measure anything, right? You understand that? You're just going to measure. So this is a dynamic resistance between the base and this right here. That only comes into play if you bias it with both. So what we're going to do, if I come over here, let's say if I have 10 volts, and let's say this is 5K, and I come up here and I can adjust that right there until this right here gets up, this goes to 5 volts. What does that tell me? That tells me that those two resistors are exactly equal to each other. You understand that? I have no idea. So as soon as that hits 5 volts, I know that my rheostat is 5K. I know it. So this is what we're going to do. We're going to set it. We're going to come over here and we're going to put a resistor right here. We're going to put a pot wired as a rheostat. I'm going to set it to 0 volts and I'm going to measure my output. Then I'm going to, so let's say it measures, what's it measuring right now? 560 millivolts. As soon as I start adjusting that pot, the output is going to start dropping down. When it gets down to what? What's 1/2 of 560? 280. Is that right? When that sucker gets to 280 millivolts, I know that the resistance of that pot is equal to the resistance of the input of the amplifier when it drops down to 1/2. Then what we'll do is we'll come out and we'll take out, we'll disconnect it, and we'll measure the resistance of the rheostat. So I got another pot up here. So how do I wire a pot to act like a rheostat? I'm supposed to have a number up here. So where am I going to put this thing? I'm going to have to come in and this is another reason why we need to have this spread out a lot more. Y'all understand that though? Are y'all okay? Yes or no? Does that make sense? So we'll start off by setting the pot to 0. We'll look at the output and then I'll start adjusting the pot so the output drops down to 1/2, which means my input signal has dropped down to 1/2, right? You understand that? And then we can come in and we can measure the ohms on the resistor. So here's my input right here. So pop this off. Y'all not seeing what I'm doing. So this is the one going to my base. Then I'm going to come in and take my pot and make it act like a rheostat. We connect the wiper to one side, so let's do that one. And then now this will go over. Excuse me? Look it up this way. Okay. So that works. So what I want to do is I'm going to replace this wire with my pot. The 10K pot. It's here. It's here. Bring this one back. So this is our maximum output. Let me bring my scope back up. So I'm gonna just move up, I'm gonna move channel 1 out of the way. We'll trigger on channel 2. So we can measure this a lot more accurately. That's maximum right there. I'm touching it. So this is maximum. Okay, it'll 50 millivolts per division. So can y'all see it? 1, 2, 3, 4, 5, 6, 7.2. Times 50 millivolts. So what's it measuring? What's that? 100, 200, 300, 350, 350 something over. Okay, so divide that by 2. This is going to be hard to do because when I touch my pot, it picks me up. You'll see that. So, divide that by 2. What that give me? 180. Got the out. So what we're doing is we got V out set to its maximum. And then what I'm going to do is I'm going to, in fact, we could bring V in up a little more if it's easier to measure. And this is maximum. So right now I have my 10K pot set to 0 ohm. And I'm measuring the output. I'm going to start adding resistance to my 10K pot until this drops down to 1/2. As soon as it drops down to 1/2, I know the resistance I have set on my rheostat is the same as the input impedance of the amplifier. Then we'll measure the resistance of the pot to see what it measures. So this is 0 ohms. Okay. In fact, I can turn off channel 2. And what do we measure? 350, 300, 360. And then we're going to come up here. I'm going to adjust this, or try to, until it drops down to 1/2. So 50 millivolts per division. And I want to get down to what? 180. 1, that'd be 100, that would be 200, that'd be 250, about in the center of this guy right here.
It's a little below 0.
If I keep adjusting, but it's not AC, so it's going to keep moving on me. And as soon as I touch it, it picks up. How far do you say, Mario?
So if you want to, so
Yeah, that'd be 150. About it. Yeah. Okay. So that means the resistance of my pot wired to the rheostat is equal to the input impedance of the amplifier. So I'm going to turn it off. I'm going to come over here and take my pot out. Keep it hooked up like a rheostat. And measure it. I could probably do this. So here's my meter lead. So I jumped it across two of them. Then I'll measure over to this guy right here. So the input impedance is about 8K. I thought that's a lot higher than I thought it was going to be. That's like it's not bypassed. It is. Yeah, it should be. Yeah, measure 8K. No, because if one of the resistors open, it would cause a different problem, and I think that's the next part of the lab is troubleshooting, right? So write that down, guys. We're not going to do anything else on that. So what's the rest of the lab? Yeah, right on it. Okay. For the measure. No, it's the game. AD. I'm sorry, not AD. I'm sorry. It's RN. I get it right. I'm sorry. It's RN. So we calculated around 4K and it measures around twice as much. So it wants us to remove C2 from the circuit. So we're going to simulate an open C2, right? Isn't that step 8? Of course, we know that the input and output are 180 degrees out of phase, right? That's what it's, number 7. Yeah. Number 8 says remove C2 from the circuit, measure the AC signal at the transistor's base. So we're going to remove C2. What's going to happen when we remove C2? Gain's going to drop way down, right? So if the gain drops way down, that's a good indication that we might have a problem with C2. So let me bring the oscilloscope back up. So this is the output. Let's swing the input back down. That might have been why the gain was off, because the input's not 10 millivolts. In fact, technically, we could have done it with a lot higher voltage. Okay. So here we're going to take out C2, which is the bypass capacitor. So here's the bypass capacitor. So we're triggered on, so I'm going to adjust it down so we can see it. Boy, my amplifier got really noisy. So my scope's having problems on what to trigger. This scope don't have the ability, my other really nice scope, it's got a filter, so you can put a filter on it to filter out the high frequency component. So, but we can measure it. So I put 10 millivolts in. I've got it on 5 millivolts per division. It's measuring 5, 10, 5, 10, 15 millivolts. So the gain is way down. That's a gain of, it's only a gain of 15. Something happened a while ago. We had a gain of, no, that's not even a gain of 1. Let me check our bias first. Oh, hold on. Yeah, guys, our gain, a while ago we had a gain of 3, but this thing, and all my bias dosages are still right. So so we removed, so here's the bypass capacitor in there. Here's my gain. There's my output. I'm going to remove the bypass capacitor. So what happened to our gain?
Lower, much
Much lower. Of course, our input impedance went up. Replace C2 and remove RL.
Higher. The voltage,
And why is that?
the voltage needs to be, this voltage goes up.
Yeah, because now it's going to be RC over RE prime, right? A while ago it was RZ or output. So here comes the load. It'd be easier for me just to move this. Oops, can't do that. Here goes the load. Okay. And the gain went up. That was step 9. I mean, I'm sorry, that was 9, right? Yeah, because we removed the load, yeah. What's going to happen when I open RE? By the way, if we had measured the bias voltage, everything would have been exactly right. Okay, so what should we expect when we open RE? Here we're going to measure the voltage. Were we supposed to measure before? Okay, so let's go back. I'm sorry. So here's the scope. This is C2 open. So let's measure our bias voltages. Here's my base voltage. It's sitting at 1.75 volts. You know, see my meter? Here's my emitter voltage. It's 1.1. I think it's 1.05 volts. Are we okay? Okay, then what I'm going to do is now it's back to normal. I'm going to open up the load. Gain goes up. I'm going to measure my bias. What do you think my bias is going to do? Mario says it's going to go up. No, it's not. What was done so far has nothing. Is R1 still in play? Is R2 still in play? Is RC still in play? Is RCE still in play? So all those fixed resistors, those are your bias resistors. So here comes my bias. So here's my base. 1.75 volts. Didn't affect it at all, right? Okay. Here's my emitter, 1.1, which is what it was a while ago. So what we've done so far has nothing to do with the bias. So the bias stays the same. So this is telling you, okay, if my bias is the same and my gain drops down, well, what would be the first place we'd do it? Well, I look at that dang bypass capacitor. First of all, I'd see if my input was right? You understand? Okay. I'd check that bypass capacitor, because that changes the gain, right? What if the gain goes up and my bias is correct? Well, that means I'm going to look at the load, right? You understand what we're saying? But the next thing I'm going to do is I'm going to start screwing around with the bias. So step 10, what am I going to do? I'm going to open RE. So let me hook my load back up. And I'm going to open RE. Wait a second. Where's my output at? So my bias. Okay. Sometimes it does. So now when I measure my bias, okay, so I got 10 volts there. Okay, so it's okay. So my resistors are pulling that. Okay. So now we're going to open RE. So here's my output. Output's gone. Which is what we expected, right? Because now we have no IC. I'm going to come up here and measure my bias voltages. This has gone up a little bit. Here's my bias on my resistor. This is hard to do. See if I can do it like this. Let's open it right here. So here, we're expecting about 1 volt. Now when I measure my emitter with that resistor opening, it's measuring the same as my base. In fact, it went up a little bit. Now why am I measuring anything at all? Because I still have a junction between my what? My base and my emitter. But there's no current flow through that junction now. So the 7/10 volt is out the window because there's no current flow through it, right? You understand? So this guy here is measuring the same as the base, and the only thing that could happen is that that resistor was open. Oh yeah, you're looking kind of strange. Why?
I would assume it would have been zero.
Why would it go zero? I'm not opening up. I'm opening up that resistor. We still have a path. So I'm coming over here.
I understand the base
I don't want it.
selector would be still have value, but the emitter, the resistor also would have both both.
First of all, I'm expecting the voltage drop across the resistor to equal to the applied voltage. Right? You understand? So what I'm doing is I'm opening this resistor. I'm opening RE. Oh, sorry. I'm wrong thing. So I'm opening RE. And I'm measuring right here. So I'm measuring 1.70 volts right there. I'm measuring 1.78 volts right here. So it means there's no current flow through that resistor, right? Because, understand what I'm saying? Yes, no. So the 7/10 volt is gone out the window because there's no, so if I was to come over here on a diode, like that, and I was to put 10 volts right there, and I don't hook this side up to anything, and I come over here and put my voltmeter right there, it's gonna measure 10 volts. Because now it's not a forward bias junction, it's just a piece of silicone in there that has no current flow to it. And that's what people have problems understanding. If you have no current flow through a device, then that device is not going to drop any voltage, but I still have a connection to the top of my watt, to the top of that capacitor. So I measured 1.78 volts right here. Notice it went up some because we lost this resistance. And I measured 1.78 volts right there. Two things could cause that. The base to emitter could be a short. It could be shorted, which we have that happen. But we know that's not the fault. So I could come over here and I could put a piece of wire and it would do exactly the same thing. Because it's not dropping any voltage. But here we know the problem we're putting into it. We're not trying to troubleshoot. So basically on most of these things, when you make these bias measurements, most of the time it's going to give you two components. And what we do is we try to eliminate one of them, right? You understand? Yes or no? So y'all know why we got 1.78 volts right there. Because that diode, that P-in junction is not acting like a P-in junction because it's not forward bias, it's acting like a resistor. And how much voltage is dropped by a resistor if it has no current flow to it? Zero. So that means I got 1.75 volts on the base, and there's no current flow through the diode to make it drop 7/10 of a volt. It's acting like a piece of silicone. It's not acting like a P-in junction. And we're seeing that 1.78 volts from the other side. Okay, so what are we going to do next? Of course, I dropped my lab book on the thing. So the bias on the base went up. We was expecting 1.5 volts. I mean 1.7 volts. It went up to 1.8 because now we don't get that resistor out there. Okay, I'm listening. What's next? Yeah, I'm sorry. Let's measure the collector voltage. So here comes the collector voltage. Oops, don't think it. So we just proved Kirchhoff's law wrong. No, we didn't. The transistor's cut off. So I'm going to come up here, I'm going to so if I was going to do Kirchhoff's law, so here's the collector voltage. It's measuring what? 10 volts. Here's the emitter voltage. It's measuring 1.78. If I add 10 plus 1.78, that gives me 11 volts, 11.8 volts. And we're only applying 10 to the circuit. Well, the transistor's cut off, guys. Where's the 1.7 volts? Is because there's no current flow through the P-in junction, right? So this wouldn't be added to the 10 volts. But it appears to make Kirchhoff's law invalid. So that's the voltage across the collector. That's VC right there. What comes next? So let me put my base resistor back in there. So what should happen when we open R2? Of course, this don't even make any difference about the transistor. I mean, this is, so I'm not going to write all those values in because this would be true no matter what. So we're going to open R2. So I've just screwed around with the bias. So what's VB going to do?
Yeah.
Huh?
You won't be able to get it.
Why not?
Use that.
Well, there's gonna be something right there. So let's say I come over here, and of course it's not gonna be true because we got another thing going on here. So guys, if I've got 10 volts right here, and this resistor box opens right there, what am I gonna measure right there?
Well,
It's a series circuit. I've opened a resistor in the series circuit. How much current flow is through there? Zero. How much current is, how much, so V is equal to I times R, okay, then V would be equal to 0 times 47K. What's that going to be? 0. So this guy drops 0 volts. I have 10 volts right there. This guy drops 0 volts. We did up with 10 volts right there. Now that's not true. So I know it can't be 0. But what we have is we have a forward bias P junction. So our voltage divider went from this, which was 47K, Rich, and 10K. It went to this. It went to 47K to beta. It went from 47K to 220K. Oh, I'm sorry, 22K. No, 220. Because that resistor in the emitter junction is seen as times beta. We've already saw that, right, on the screen. So what's the base voltage going to do? It's going to go up a lot, which should cause the transistor to saturate. Y'all understand why? Yes or no? So the base, normally we ignore the emitter resistor because it's so big. Here I can't ignore the emitter resistor because now it's setting the base voltage. I've lost something again. Okay. Okay, so here's my meter. Okay. So right now my base voltage is measuring 1.75 volts. And we're going to open up R2, which is the 10K, right? Pull my thing out. You see where my base voltage went to? So this is when it's in there, so I can think about that. So here's the resistor in there. It's measuring 1.75 volts. Here I'm going to open it up. And it went up to twice what it was supposed to. I'm trying to see what the output signal would be. The output signal is probably going to. So my emitter voltage has gone up to, instead of being 1 point something, it's gone up to 2.6 volts. My collector voltage is, my collector voltage has dropped down to 2.75, so the transistor's going into saturation, right? Understand that? And I was trying to look at the output signal to see what it would look like, but it's going to be all distorted. So where's my input at? So, by the way, to show y'all how sensitive a scope is. So this 60 cycles is being induced into me, and my oscilloscope is measuring it. Thank goodness. That right there is what makes that AC signal that's being induced into us is what makes these screens right here work. So that's what it's picking up. Picking up that AC signal up there. And it's picking it up in a metric. So the whole display is a bunch of rows and columns. And then wherever you touch, it gets a signal. It's a print, and that knows where you're at. It's pretty good. So this is why these, we call it a capacitive effect. So this is me. So I don't know where my input signal's at. So there's my ground.
So when the resistor RC is open, it current is 0, right?
I don't know. No, there's a path through there. So what we have, what do you mean when a resistor opens? So that would be like me coming over here on this circuit right here. So this is the circuit. We've got another path. So what I've got is I originally come over here and I've got this circuit right here. I got this, which is a 47K. And I've got this, which is a 10K. And then I've got this, which is through my transistor, and I've got this resistor right here. Now, as soon as we go through that times beta, we're assuming a beta of around 100. So what I do, we call it the 10-to-1 rule, and we proved that the other day. I came over here and I said, okay, I'm going to come over here, let's say this is 10K. Well, let's just do this. Let's say I come over here and I have a 10K in parallel with 100K. What's my total resistance? A 10K in parallel with 100K.
You got 90,
Yeah. So what we're doing, since this resistor in the emitter is seen times beta, when that R2 is in there, we just ignore it because it's not. Notice it. We calculated 1.7 volts and we measured 1.7 volts because that sucker is being seen as a 220K over there. So what's a 220K in parallel with a 10K? Well, it's 9.99999K, right? But as soon as I open that resistor, now here's my current path. So now I can't, that's open. So now I got this 220K over there. So now I got 220K in series with this, and my whole voltage divider is gone. Right? You see that? So now my voltage is double, right? You understand that? Is that so? Am I doing it? I'm not. I'm sorry. 22K. It's not 20.
So what was the value of the transistor at that point?
Let's see what was the value of the transistor.
Okay.
Well, I don't know what when you say what was the.
Transistor cut off that.
Well, we know if the output goes down. So VC, we can look at VC. Okay. So we know. Let's figure this. We know this resistor right here is dropping 1.7 volts. Okay. So I'm not sorry. It's dropping 1.05 or something like that. So when I come over here, first of all, we realize now why did the voltage go up so much? Because now my voltage divider that's setting my base voltage looks like this. It's a 47K, and this right here is a 22K. Because it's times beta. Okay? So what would the voltage be right there? In fact, we could probably calculate later. Wait, that's 3 digits. I think so. 2.2.
And info voted was, what was it again? Info?
Yeah. So what's 2.2K times 100? It's 220, right? No. What's 2.2K times 100? 20,000. So it's 220K. So I didn't know my zero was in. Yeah. No, you're thinking about the base. The base is not the base is not what's active. The base is what's on that collector over there. So when we come over and measure on our collector, oh, look, can you see my meter? So this is Kirchhoff's law. So this is on my emitter. Okay, this is on my collector. So VCE, we're actually doing more than so VCE would be DC, which would be 2.75 minus DE, which is for some reason is 2.6, but you can't do much more than that. So this sucker is flat saturated, right? It's less than 1 volt. It's actually a negative value. So if I look at my output's doing nothing. Well, that's not true. I can't get my input anymore. I don't know what's going on. So what we're saying, if R2 opens, the transistor is going to saturate. Here. Okay, there we go. Okay, what's the next thing that's going to happen? Let me put R2 back there. Check my time. So we're back. What's gonna happen next? What we're gonna open up next?
That was it.
Huh?
That was it.
Well, let's go ahead. Let's open up, what's the top resistor? R1. So what should we expect when we open up R1? So if R2 opens, we saturate. What would you think would happen if R1 opens? What would my base voltage go to? So here we have a path. When R2 opens, we move over to this path, right? You understand? What I'm going to do is I'm going to come up here and I'm going to open up this guy right here. So what would my base voltage go to? So is there a path, any way current can get through these two resistors right here? Is there any path that it could go up to there? No. No. So what would my base voltage go to? 0. What would the transistor do? Gonna cut off. So here's R1. So that's the 6.8K, right? Base goes to, here's the base voltage. Let me put my meter up there. Base voltage goes to, can y'all see it? Base voltage goes to 0. Collector voltage goes to, I can't do that, Rich. I pull my power supply. Okay. Base voltage goes to 0. And then the collector set at 10 volts. So if R1 opens, it cuts off. If R2 opens, it saturates. If RE opens, then or if the capacitor opens, we lose all our gain, right? If RC opens, the gain drops down a lot. And what was the other one? Okay, guys, so y'all needed to go ahead and answer y'all's questions. Y'all can do it here. I've got a meeting I got to go to at 12. So, but, yeah, if y'all want to come in tomorrow, work on your labs, that's fine. Yes, I'll come in tomorrow if somebody wants to come in. But don't make me come in and be here by myself.